Okay, let's begin. This video's topic aims to tackle equilibrium constant expressions. Provides a little bit of a review of their form and how do you manipulate these equilibrium constant expressions, which becomes a little bit useful when you want to try to generate an equilibrium constant for a reaction that you might not have a value for, but you have some other reactions that you can combine in a certain way, and you do know the equilibrium constants for those reactions. So we'll see an example problem of that in a few minutes, but before we get to that, let's just review the form of the equilibrium constant expression and some rules that we can use. I'm going to rate this a pretty important topic for your semester and also for your final exam. So setting up the form of this expression is going to be pretty crucial for you to solve problems when you reach the equilibrium part of your course. So for any chemical reaction which is given in a generic form such as this one, we've got reactant identity A and B, capital letters, to yield products C and D. Those are the actual substances of the molecules, or the uppercase letters, and the lowercase letters are the stoichiometric coefficients that would be written out in front to balance the reaction. So if we treat this with a double-sided arrow as a true equilibrium, we can write an equilibrium constant expression that describes the position of that equilibrium. And of course we do that through using a form of an equation that looks like this. K is the equilibrium constant for the reaction. We express that as being equal to a ratio of the products divided by the reactants. Products over reactants is what I like to say. And the square brackets here are indicative that we're dealing with the concentrations of the substances. Now in analytical chemistry class, very frequently, that's going to be the molar concentration of the substance in question. If it's some sort of aqueous ion, for instance, okay, it's the molar concentration. It can also be partial pressures of gases. If so, that would be the partial pressure of the gas expressed in bars. Again, if it's a solute like an aqueous ion, it's going to be in moles per liter, these terms. And then importantly, pure solids, liquids, or solvents are going to be excluded because they assume to have an activity of unity or 1. Which actually brings me back to another point before we go on. As you progress in, say, a junior level analytical chemistry course or quantitative analysis course, you might begin to learn that the terms that are in these equations are actually not truly just molar concentrations. They're actually supposed to be something called the solute activities. It's given a symbol lowercase a very often. In this video tutorial, we aren't going to consider not going to consider activity. However, in a later video, we may consider that, so you can look that up if you're interested in it, okay? But it turns out these are really meant to be the activities of the substances and not just the molar concentrations. But for now, we're just going to abbreviate and approximate the activities as being equal to the molar concentration. So we come to the familiar form of the K expression, the products over reactants multiplied by one another. And note here that our superscripts C, D, A, and B, those are those numbers that were out front. Those are our stoichiometric coefficients. So we actually have to take the concentration of substance C and raise it to the power of the stoichiometric coefficient. Same thing for D, same thing for A, and for B. Okay? So this number K then describes the position of the equilibrium. If it's a very big number, that basically means that we've got a lot of C and D present in the reaction system once it reaches equilibrium. Okay, so this always describes the equilibrium position. So once it reaches equilibrium, we would have a lot of C and D if K is a big number. We'd say it's product heavy, or it proceeds far to the right. It would be lingo that would be used. However, if K is a very small number, that would mean that we do not have very much C and D, and consequently we have a lot more A and B, relatively speaking. Okay? That would make K very, very small. In this case, we would be very reactant heavy. The reaction would be said to lay far to the left, or the equilibrium would lie far to the left. Okay? So the magnitude of this number describes basically whether we mix these guys together, if we get a lot of C or D, or if we have a lot of A and B. If K is a big number, we got a lot of this products, if K is a small number, we've got a lot of A and B, relatively speaking. Okay, so that point is also important. So what do you need to know? You need to know how to define K. That's very important because you're going to use this all the time in your analytical chemistry class once you get into talking about equilibrium. You should also know the magnitude of K and how that relates to whether or not we're product heavy or whether or not we're reactant heavy. Again, if K is big, mostly product exists. If K is small, mostly reactants exist. And that's a lot of what you should take from this first introductory slide. Hopefully, that's a bit of a review from what you've seen before. There are some other rules to remember about equilibrium constant expressions that may prove to be useful for us eventually, okay? The first rule is that the equilibrium constant for a reversed reaction is simply the reciprocal of the original equilibrium constant. Reciprocal, of course, is 1 over K, which is the original constant. So to give you an idea for what this looks like mathematically, consider this equilibrium, which would be for a monoprotic weak acid that we call HA. It's kind of a generic way to show a monoprotic weak acid in class, okay? Now we can donate a proton to make H plus and the conjugate base A minus. That process is governed by a K. We usually call that Ka for the case of donating an acid, a proton, okay? If this reaction has a K value of 1.8 times 10 to the minus 5, the reverse reaction, that is where we flip-flop reactants and products, will have a K that is the reciprocal of the original. See what we've done? H and A now are written on the left side, and the product HA is written on the right, whereas before it was over here, so we flip-flop reactants and products. To compute the K for this second reaction, just take the reciprocal of the original. So that would be equal to a little over 55,000. That makes a lot of sense if you think back to the form of the equilibrium constant expression that we learned about on the last slide. If you flip-flop A, B, C, and D and make what was the reactants products and what was the products reactants, it makes sense that all you do is you flip-flop this ratio. So of course the reciprocal should result. That makes a lot of sense mathematically. There are some other rules to remember as well. This is the second rule. There will be 3. In this case, if the stoichiometric coefficients of an equilibrium reaction is multiplied by an integer, that's a whole number like 2, 3, 4, the equilibrium constant will be raised to that integer to generate the new equilibrium constant value. So say for instance we go back to that reaction in which HA donates a proton to make H plus and A minus, the conjugate base, okay? That's given an equilibrium constant K1. On the last slide that was 1.8 times 10 to the minus 5. The exact value is not terribly important because this goes as a generic sense, okay? So say for some reason I want to take this entire equation and multiply by an integer. Perhaps that integer is 3, like I've shown down here below. It could be 4, it could be 5, it could be 2. It could multiply by 2, but I'm going to multiply the entire reaction by an integer. If I do that, my new equation is 3HA, equilibrium arrows, yields 3H plus and 3 copies of this. If I want to know what the equilibrium constant reaction is for this reaction that's multiplied with the 3's out front, the new equilibrium constant is equal to the original constant raised to the power of the number that we multiply the equation by. So here we're going to raise it to the 3rd power because we multiplied the equation by 3. If I had multiplied it by 2, that number here would be a 2. If I multiplied the whole thing by 6, this should be a 6. You take the original constant for the original unmultiplied reaction and raise it to the power that you multiply the equation by. And it's that simple. Now you may ask, why would you ever want to do this? This doesn't make a whole lot of sense, okay? Like, where would you use this? Well, in a second, after we discuss the 3rd rule, we're going to be talking about combining different reactions to generate equilibrium constants for new reactions that we might not have data for. When we do that, we might need to multiply a reaction, in some cases, by a constant so that we can cancel things out. And that may not make a whole lot of sense right now, but I think it'll make a little bit more sense in a few minutes once we look at the sample problem. In such cases, you may need to do this, and you may need to employ this rule. Let's talk about the third and final rule for manipulating equilibrium constants. This rule is going to be for the case in which reactions are going to be added together. I just mentioned that in some cases we'll want to add several reactions together to generate a new reaction that we want to know the equilibrium constant about. This is the summation rule that we're going to use. So it's actually going to be important to remember this one as well. When reactions are added together or combined, the value of K for the combined reaction is the product, results from a multiplication operation, of the original K values for the reactions which were combined or added together. So let's consider an example here at the middle of the slide, and then we're going to consider a more, slightly more complicated chemical example. In the example here in the middle, I've got a first reaction, HA, yielding a proton and A minus. Donates the proton and makes A minus. In the second reaction, these are hypothetical too, they're not real, okay? In the second reaction, they could be real, but we're going to say they're hypothetical for our purposes. The second reaction, H plus combines with your carbon atom, we'll say, to make CH plus, okay? Now, if I want to take these two reactions and combine them or add them together, I can do that to generate a third reaction. That's shown down here in the bottom. And see what I mean by that is I look for substances that appear on both sides of the arrows. Like for instance, this H plus here and H plus here. There's one on the right, there's one on the left. So they kind of cancel each other out. There's no net change in H plus when I add these together. I also like to think of that mentally as this H plus being consumed in the second step of a multi-step reaction process. If you want to think of it that way, that might be useful mentally, okay? But the net result of it is I make an H plus, and then I use it, so there's no net change in my H plus, and all the other substances that are present just kind of come down and combine in the overall net reaction. When I combine these two, I just add them together, basically. Summing them, if you want to think of it that way. So HA comes down, the C comes down, the CH plus comes down. There should be a plus right here. It's a typo to not include that because the CH plus comes down and the A minus comes down. Everything else just comes down. Now, I don't know anything about this reaction. I don't have the equilibrium constant for it. But maybe I want to know what the equilibrium constant should be. Well, this rule tells me that if I want to know the K for this reaction, all I need to do is take K1 times take K2, and that's my equilibrium constant for this reaction. So I may not have data in my table for this, but if I multiply K1 times K2, because I sum these two reactions to make this rule tells me that the equilibrium constant I get should be representative of the constant for this particular reaction. So this is actually kind of a useful rule because you can combine other reactions to generate a new reaction. You don't know anything about this, but based on the product of the case, you can predict whether or not this would be product heavy or reactant heavy. So it's kind of a cool thing to be able to do. Now with that said, what I'd like to do is work one sample problem at the bottom of the slide. You could encounter something like this during your course in chemistry. Okay? Now what this problem is all about is shown right here. What I'm asking is what is the K for this reaction? Now, what do I mean by this reaction first off? Well, to give you some background, what I'm going to ask you here is to consider citric acid. Citric acid, structure here, it's going to be treated here as a triprotic acid, weak acid, triprotic weak acid. Proton here, here, and here in the structure. Okay, you can see the carboxylic acid groups if you're familiar with that. 1, 2, 3. You could recognize those as weak acid groups. Now, because there's 3 protons, if you look up data in a table for the acid ionization constant, or the Ka for citric acid, you'll find 3. You'll find Ka1, which is 7.44 times 10 to the minus 4. You'll find Ka2, 1.73 times 10 to the minus 5. You'll find Ka3, 4.02 times 10 to the minus 7. So Ka1, 2, and 3. These are the equilibrium constants that describe the donation of the first, second, and third proton sequentially, okay, from citric acid. Now, I can find that information in a data table, but what I really want to know about, for my purposes, is this reaction. What is the K for this? Now, first off, I wrote this in a shorthand notation to sort of save time and space here. But I wanted to find what I mean by this. This H3C is meant to be the fully protonated molecule of citric acid, where it's got all of its protons. Okay, so that's the citric acid fully protonated, is my H3C. 3H plus are my 3 protons that result from the donation of all 3 of these guys. Okay, and C3 minus, I'll call that my triply deprotonated citrate, or fully deprotonated citrate. Okay, it's where all of these acidic protons are gone. They've been deprotonated. So I'm basically wanting to know what is the equilibrium constant for the citrate molecule losing all 3 of these protons to form the triply deprotonated citrate. Now, I don't have that information. This is for the first proton, the second proton, the third proton, but I might be able to write a series of reactions that can generate this overall equation. So let's see how we can do that. So the first thing I'm going to do is write 3 reactions. The first reaction, I'll call that reaction 1. I take my fully protonated citric acid, that's this molecule as written over here on the left, and I deprotonate 1 of the protons to make H2C minus. In the second reaction, I take the H2C minus that was formed, deprotonate again, yielding HC2 minus. Finally, in the third reaction, I take this, deprotonate a third time to make H plus, and C3 minus, my triply deprotonated citrate. So I have reaction 1, 2, and 3. Now, if you're familiar with the equilibrium constant expressions for Ka, which hopefully you've at least seen before, okay, you realize that the reactions that I wrote here, here, and here for reaction 1, 2, and 3 are actually the same as these Ka1, 2, 3 expressions that are over here on the left. They're the same reactions. So reaction 1 corresponds to the Ka1 expression. Reaction 2 corresponds to the donation of the second proton, it's the Ka2 expression. Reaction 3 is the Ka3. Okay? So the beauty of this is that if I combine these 3 reactions, let's see what we generate. So first off, does this cancel out? It does not. So I have to write the H3C. However, the H2C minus cancels, as does the HC2 minus. So there's nothing else I need to write on the left. On the right, I see I've got 1, 2, 3 copies of H plus and 1 copy of C3 minus. And lo and behold, by adding these equations together, I have generated the equation of interest. The beautiful thing is that, as I've already mentioned, I know the equilibrium constants for these 3 reactions because they were given to me in the problem. I've recognized each of these reactions as the K expressions for Ka1, Ka2, and Ka3. So to solve for the K of this reaction, all I need to do is take the product of Ka1 times Ka2 times Ka3. I multiply these 3 numbers together. Okay? If I get a calculator out and I work that, I find the result is 5.17 times 10 to the minus 15th. And that's of course a very small value for K. Okay, meaning that we would be very, very reactant heavy, if you will. So if I take, basically what this means chemically, is if I take this molecule, triply protonated citric acid, and put it in a beaker, this reaction is not going to proceed very far at all. I'm not going to have very much of this triply deprotonated citrate. If I wanted to find the equilibrium concentration, I could, based upon this number, I could work an equilibrium ice table that's considered in a different video, okay? But I'm not going to have very much of it because this number is a tiny, tiny, tiny number, okay? So that's what this tells me chemically. If I wanted to find the amount, I could, working the equilibrium ice table. And that in itself is kind of an important point to make here, okay? Because you might wonder, like, why in the world would I ever do this? Like, it seems kind of strange that I would add these equations together to generate this new reaction. Well, what if you wanted to know the standing concentration of triply deprotonated citrate in a beaker where you add citric acid to a certain concentration? Well, you could compute it using this type of approach and then subsequently an ice table, okay? So that's where you might want to use this kind of thing in terms of calculations. But nonetheless, what we've done here in this video is we've successfully talked about 3 different rules for manipulating equilibrium constants. We talked about this one, which will frequently be used. This is adding the multiple reactions together. You just take the product of the equilibrium constants. We also talked about multiplying a reaction by a constant, say 3. If you do that, you have to take the original K value and raise it to the power that you multiply by. I think you can see how you might use this reaction now that we've actually worked this example, or used this case when we've worked this example, right? Because in this particular case, I gave you an example where the reactions kind of behave nicely and they just added together to the desired. But what if you had a reaction where you had to multiply the first one by 2 or by 3 to make the desired reaction? Okay, well then you might have to do some work before you invoke this rule. You might have to multiply this reaction by 2 or by 3. And in doing that, you need to use this rule. Okay, you have to do that first. We also talked about the rule for reversing reactions. And this one's pretty easy, right? You just take the reciprocal. That makes a lot of mathematical sense. We talked about the form of the equilibrium constant expression. Again, usually in our class we'll use molar concentrations of solutes or the square brackets here, okay? But we all need to know this form and how to write that. So with that said, it concludes this video on equilibrium constants. Hope you found it useful. Please see the other video on equilibrium ice tables for a more thorough discussion of how to solve equilibrium problems.